Hello there. Just thought I'd try to explain where the Poisson distribution comes from. It's a probability distribution function. It has unique characteristics, and it has its origins actually in the binomial probability distribution function. So this guy, obviously, hopefully French. His name was Poisson, which of course is the French word for fish. I lovingly call these fish distributions. Nonetheless, he and others like him were studying what happens if you had an infinity number of trials in a binomial probability distribution. Recall, in the binomial probability distribution, you need to know the probability of success, and you need to know the number of trials whenever there's an outcome that could or couldn't happen. We're going to keep the binomial distribution, but we're going to allow the number of trials to go to infinity. Now what I have on the screen is a bunch of mathematical mumbo-jumbo. It's in the notes I provided for you on the class page, for those of you that are elite members of my class. If not, just screenshot this and you can see some of the foundational elements that need to be background knowledge in order to make this proof work. The first is the limit as n approaches infinity of 1 minus m over n to the n equals e to the negative m. If you remember the origins of the value of e to the x power, or just the e, the number e is 1 minus 1 over n to the n as n goes to infinity. So you can see by adding the m, it changes the rate of change. Anyway, that's a known, that's a necessary fact. And here's another one which is a little bit more abstract, and here I'm going to ask you to just take my word for it. If we have n factorial over n minus x factorial times n minus m to the x power, and we allow n to approach infinity, that in fact does approach 1. You can even demonstrate that on Desmos by putting in constants and showing that this works no matter what, if you allow n to get really, really large. So anyway, these are the proofs of those two statements, and now just want to briefly walk you through and show you where the Poisson distribution comes from. First of all, I hope. Alright, so here's your binomial probability distribution function. We have n trials, x outcomes desired, and the probability of success is p. Changing the combinatoric into its formula, that's where we get our factorials. And then we have m over n. So the reason this happened is because m, as we know from a binomial probability distribution function, the mean is equal to n, the number of trials, times p, the probability of success. So if you solve for p, you get p equals m divided by n. So instead of p to the x, we have m over n to the x. Similarly, 1 minus p to the n minus x. So after doing a bunch of mathematical gymnastics, you can see we break up the exponent here, so we have two different terms, and we're doing some rearranging of the terms here, basically just switching around to make our suitabilities happy. Now, I'm not going to bore you with the rest of this. I will say again, either read the notes that I provided or screen capture this, but see if you can follow the logic train that comes around until we get to here. At this point, we have this odd expression, but we are now going to allow n to approach infinity. There we can take the e to the negative m that we saw on the previous slide, and we have this part right here, which we said is equal to 1. And so therefore, if we have infinity number of trials in a binomial distribution, and we can see how the mean got worked in, we have mean to the x, which is the desired number of outcomes, over x factorial plus 1 times e to the negative n. That is the formula for the Poisson distribution. Now it's abstract and it's kind of weird, but I will tell you, first of all, the most common usage for Poisson distributions are for events that are considered to be rare. For example, if you live in a northern climate, you're no stranger to having a snow day where you don't have to go to school because of a blizzard or a snowstorm or an ice storm or whatever. Well, those are in fact rare events, and you could, if you wanted to know the probability of, say, next year there are going to be 3 snow days, you can, if you had the historical data of the average number of snow days per school year, you can predict the probability of having 3 snow days next year using this Poisson distribution. So here's another example of where that works. We have a wire manufacturer looking for flaws, and their experience suggests that there's an average of 1.8 flaws for every meter in the wire. So, determine the probability there's exactly one flaw in 1 meter of wire. Well, that's easy because there's 1 meter of wire, and we were given a mean of 1.8 flaws per meter of wire. So we know that the mean is 1.8 in this case, and we're looking for exactly one flaw, so that's our desired outcome, X. That's all we need to know to be able to use this distribution to answer the first question. We establish the mean, and we use mu for that, or m, and then we actually say that X distributes as a Poisson distribution, that's P sub 0, and then all we need is the 1.8. Remember, we don't need number of trials because we let that go to infinity. So 1.8 is the mean, so this is my way of saying we distribute on a Poisson distribution with a mean of 1.8. We are looking for the probability of exactly one flaw, that's probability of X equals 1, and we can put the mean to the X power times e to the negative mean all over 1 factorial. That's the X factorial, of course. And that turns out to be 0.29753. So there is almost a 30% chance that there will be exactly one flaw in every meter of wire, which means this manufacturer is not doing a very good job. Now, this is the important part. Determine the probability that's at least one flaw in 2 meters of the wire. Here's where you have to do a little bit of adjustment. A common mistake in using Poisson is to take the average in the paragraph and use that exclusively throughout the course of the problem. However, here it says determine the probability there's at least one flaw in 2 meters of wire. We have to understand that 2 meters of wire is changing our flaw mean. In other words, if we have 2 meters of wire, we should expect 3.6 flaws for every 2 meters of wire. So the mean is now changed to be 1.8 flaws per meter times 2 meters, 3.6 flaws average. So this time now it says at least one. Remember, when we have at least, we're going to take the probability of it not happening and subtract that from 1. So here again, we can go straight to the formula, and thankfully 0 factorial gives us 1, so we don't fritz out our computers, and we have a 97.3 chance that you're going to get in 2 meters at least one flaw. That goes back to that poor success rate they have over there. So one last little thing that I want to share with you is about the graphics display calculator. So I'll share that with you here. Wanted to basically show you how you can answer any question with Poisson distribution. And first I'll point out that it's under the distributions, which is above the variables key. So I will hit second and dister for distributions, and then you can see by scrolling up to the bottom of the list, you'll see Poisson distributions. Here we have the probability distribution function, and here we have the cumulative distribution function. So if you go back, how the binomial has a probability and a cumulative, the Poisson does the exact same thing. So if I choose option D for the probability distribution function, the Poisson distribution function, and I'm trying to multitask and I can't because I'm old and there's a lag, and here we go. Alright, so hit enter, and it's asking for the mean. Remember, there was 1.8 flaws per meter, and the X value I was looking for was one flaw in a meter of wire, and if we hit paste, wham, it gives us the command term, and there's the probability that we saw from earlier. We could also go 1, subtract, then we go second, dister, scroll up to option D again, enter, mean was 1.8, and this time we want the desired value of 0, so we have at least one flaw. Paste that in. Now it's 1 minus the probability of 0 flaws. Hit enter, and there again, oh, I had the wrong mean. That's why the number's not the same. I had to double the mean. So, but it's just understanding how the calculator works. That's all we're doing here. And just last but not least, we have the cumulative distribution function. Remember, with binomial cumulative and the Poisson cumulative distribution functions. It shows you x less than or equal to a desired value. So if I do cumulative, it still asks for the mean. We could have 1.8 again, and this time I could put in an x value of 3 for a random reason, and then I hit paste, and that gives me the probability of getting 3 flaws in 1.8, or sorry, 3 flaws, or 2 flaws, or 1 flaw, or 0 flaws. So 3 or fewer flaws in a meter of wire, 89%. So pretty good chance. So hopefully you find this helpful. Thanks for watching. Have a great day.